I'm increasing by 1/4 every time. So 3/4 and 1/4, you see, would be 1, and then 1 and 1/4, and so on. All right, and here, this is the pattern of the cosine curve. It's top of the amplitude 0, bottom of the amplitude 0. Next thing in line would be the top of the amplitude, and then 0, you see, and so on. Well, and then we would, of course, add these. We have 1 and 2 to give 3. 1 and 1/4, and 0 is 1 and 1/4. All right, and then we would go over and plot those points. Now, another technique is to do this, is to graph this and graph that as separate graphs, and then add y values. Let me show you what I'm talking about. I have constructed the graph of those two right here. Can you pick out which is which? I'm sure you can. All right, this is the graph of x over 2, and this is the graph of that cosine curve. All right, it's actually 2 cosine pi x. All right, here's that curve. Now, the way that we generate points for the sum of these two is to add vertical distances at every point on the graph. For example, we could take a point like, I think a convenient point is this one right here at 5. When x is 5, this graph has a y value that is -1, 2. So this is at -2. Now, I'm reading over, now notice that let's not get confused here. On my y-axis, every other mark is a full unit. So this is 1, even though there's a mark here at 1/2, you see. So this is 1, 2, 3, 4, and then the same way going down, same way left and right. Okay, so here we have -2. But on the other graph, we have 1, 2, 2.5. So we have 2.5 with -2. 2.5 with -2, that's a half when we add those two together. So 1/2, that's right here, is going to be on the graph of the sum of these two. You see, and that's how we make this analysis on and on and on. At this point, and the intercepts are really easy here because we have 0 on this graph, and then we're adding that amount, you see this vertical distance, for this other graph, and so the point will be right on that graph. All right, and then at 6, we have, let's see, we have 1, 2, and then also 3. So 2 plus 3 is 5, and so I come up here at 5, and this point is on the graph. And now we have the kind of thing where we've got this going on. Now, I'm sure that this is well, I shouldn't say I'm sure. I'm pretty sure this is a relative minimum point because I have a relative minimum point on one of the items that I'm adding. You see, that's a relative minimum point. And if I come back in this direction, I'm subtracting a little bit less in value here than I have right up here. So I think this graph is going to go up like this. In a similar way over here, if I have two tops, if I have a top here and an item on this graph, I have a relative top here, because then I start to turn down. Now, this may not be an actual relative maximum point, but it sure is in the neighborhood, you see, because that graph is going to turn down. And then at this point, at the intercept, I'm back at adding 0 with this vertical distance to give that point on the graph. And here we go with that point. You see, so it behaves like this. And then doing that all along the way, we discover the behavior of the graph of the sum of these two. Well, still, a little bit of a rigorous kind of thing to discover the behavior of that big graph. The easiest way, of course, is to put this on the graphing calculator. And that's what we want to do now. Let's look at it on the graphing calculator, and we're also going to look at the graphs of some other rather exotic-looking equations on the calculator as well. The two equations have been entered, and separately on standard settings, their graphs look like this. Now, upon adding the two functions, however, that is x over 2 plus 2 cosine pi x, we have this effect. And notice that it kind of looks like we are causing this cosine curve to take on a rather linear pattern. And that is fundamentally what happens when we add two functions like this. And we can see the situation perhaps more clearly if we take out these first two and just look at the third. Whoops, take out these first two and look at the third. You see the cosine curve is sort of taking on a kind of a linear-like pattern because we're adding the two together. Now this is not something that's terribly foreign to us. We have seen this situation in the past. That is, remember, when we had something like, oh, I could take y equals 3, I could take y equals sine x, and separately their graphs look like this. But then if I add the two together, if I take 3 plus sine x, then it almost looks like I'm taking the sine curve and putting it right on top of that, that line. You see, that is effectively what's happening when I add the two together. Now, generally, we don't see these two graphs. We just see this graph, you see, but actually, what's happening is that we're putting sort of one on top of the other. All right, let's do something a little more exotic. Let's clear this one and use another kind of pattern. Instead of fitting a linear pattern of sorts, let's fit something that's curvy. How about x squared divided by 8? And we want to fit onto that sine 2x. Now let's change our window settings a little bit. I've looked at this before, so I know that something like an x of negative 6 for the minimum and 6 for the max will look a little better, and we'll change the y to a y min of negative 1 and a y max of 5. And now the two graphs separately look like this. Here's our parabolic graph, and here is the curved graph. What we're going to try to do is make the sine pattern turn out to be parabolic in nature, and we can do that rather easily by adding the two functions together. Now, there is another way to add the two functions. We can of course enter x squared over 8 plus sine 2x, but another way to do that is to press the vars button and then cursor to the right for y vars, and we want a function, and the function we want is y1, so I'll press enter here, and now I want to add y2, and I go through the little sequence again: vars, cursor right, function, enter, and then cursor down to y2, and now I have y1 plus y2. And now the three graphs, the third graph will come on top of the other two. So we're making that sine curve take on a parabolic pattern. And if we'd like to see this without the other two graphs, I'm not going to clear these because y3 is defined in terms of the other two, but I can press enter with the icon over the equal sign and deselect these two for graphing. So the graph of the third one will come up alone. The sine curve in a kind of parabolic pattern. Well, here's another. Let's get away from this idea of adding functions, and let's consider what happens if we multiply functions. It turns out that we can define the borders of a graph and make a sine or cosine pattern go into a certain border. Let me show you what I'm talking about here. Suppose I enter 3 and negative 3, something very basic, and then we know what the sine curve looks like, but I'll enter it anyway, and we'll take a look at these. And I think I'd like to have a look at these in a different window setting. This is okay for x, but I want plus and minus 4, I think, for the y's, and the graphs then look like this. Okay, these are all the expected outcomes, but in order for me to cause this sine curve to go up to this mark and down to this mark, make this the top of the amplitude and this the bottom of the amplitude, all I have to do is multiply them together. And we've seen it a number of times before. This would then be 3 sine x. And let me take off the regular sine curve here so we can see this more clearly. But here is the graph. So by multiplying the two functions together, we are defining or describing a border, sort of, for our sine curve, and then we're placing that sine curve within a particular border. Now we can make that border look as exotic as we would like for it to look. Let's clear this one off and come up with a rather exotic looking border. How about a border that is something like 1 over x and the negative of 1 over x. And so here's the border, and I'm going to change window settings. We'll look at the border in just a second. I'm going to make my window settings x min negative 12 and the max 12, and then I'll come down for the y's and set the y at negative 0.5 and the max at 1.25. Kind of tight on the y's, but you'll see why in a minute. And these two graphs are here. Now what I'm going to try to do is get a sine curve to wiggle in between these borders. And I can do that by doing this. Just enter 1 over x times sine x. Now I would like to make this a distinct coefficient. So I'm going to go back here and I'm going to put a parenthesis around the 1 over x. I'm pressing second and insert because I want to insert an open parenthesis here. And I'll close that parenthesis on the other side. And now sine x. So all I'm doing is multiplying the 1 over x times sine x, and I am effectively putting that sine curve inside this border. This is called a damping effect. A damping effect. You know, obviously I could take the border lines off, but it kind of looks neat to see those border lines. Now remember, all I'm doing in multiplying here, remember that a coefficient of sine x is sort of defining the amplitude, and this is the amplitude of that function, and so it goes up to that mark and down to the bottom of that the reflection of that mark, and so on, and just back and forth, just bounces back and forth between that kind of graph, plus and minus that amount. And here's another one. Let's look at one more. This is the most exotic of all. This is my favorite. I'll clear these off. And my border is going to be 1.3 to the x power and negative 1.3 to the x power. And for window settings, I'm going to reset x minimum to be negative 3 and the max to be 10. And then for y, I want plus or minus 8. So negative 8 and 8. And here's the graph of the border that I'm going to create for a sine curve. I'm just going to place a certain sine curve right into this pattern, right in the middle of this pattern. Now all I need to do is multiply, use this function, you see, as a coefficient. So I will write 1.3 to the x power times, once again I forgot that to confine this within parentheses. So I'll go back and insert a parenthesis here and here. And then now I want this sine curve to be kind of wiggly, so I'll make it sine 3x. And here's the graph. So some rather exotic situations can occur here by using this damping effect. You might play around with this on your calculator and see what kind of different things you can come up with.